Hello, health research enthusiasts, to a vital investigation in our machine learning series. I'm thrilled to guide you through this episode, where we'll tackle a classification task using a significant dataset and a powerful explainability tool. I'm working in Google Colab, walking you through each step clearly so you can follow along as we classify diabetes diagnoses. Let's begin by setting up our environment and gathering our tools for this health-focused study. I start by installing the interpret library in Colab with a simple pip command. This library will enable us to explore explainable AI, helping us understand our model's decision-making process. Next, I import the necessary tools. NumPy for numerical operations, Pandas for data manipulation, and Sklearn's train test split to split our data, random forest classifier for our model, and accuracy score and classification report to evaluate performance. From interpret, I import Morries sensitivity from the black box module, our tool for global explanations, along with the show function to display results. I set up inline visualizations with set visualize provider and inline provider, ensuring our plots render directly in Colab. I also set a random seed with NumPy's random seed, set to 42 for reproducibility. With our tools ready, let's load the data. I load the Pima Indians diabetes dataset from a reliable online source, since Sklearn doesn't provide it directly. I fetch it from a GitHub repository using Panda's read CSV function, specifying the URL and defining the feature names: pregnancies, glucose, blood pressure, skin thickness, insulin, BMI, diabetes pedigree, age, and the target column, where 0 means non-diabetic and 1 means diabetic. I print the first few rows to examine the data. The first row shows pregnancies 6, glucose 148, blood pressure 72, BMI 33.6, age 50, and target 1, indicating a diabetic patient. The next row has pregnancies 1, glucose 85, BMI 26.6, age 31, and target 0, non-diabetic. This dataset includes 768 samples of Pima Indian women, with 8 features and a binary target, 268 diabetic and 500 non-diabetic cases, making it a binary classification task. Let's prepare the data for modeling. I split the dataset into features, and target X includes all columns except the target, the 8 features, and Y is the target, 0 or 1 for non-diabetic or diabetic. I use train test split to allocate 20% for testing and 80% for training, with random state 42, giving us 614 training samples and 154 test samples, approximately 99 non-diabetic and 55 diabetic in the test set, based on the dataset's 65 to 35 split. The features are all numeric, representing health measurements, and while there are some 0 values, e.g., insulin 0, they're part of the dataset structure, so we'll proceed without pre-processing. We're ready to train our model. I initialize a random forest classifier from Sklearn with 100 estimators and random state 42. Random forest classification is an ensemble method that builds multiple decision trees, 100 in our case, each trained on a random subset of the data and features. It aggregates their predictions through majority voting to classify outcomes, reducing overfitting and improving accuracy, making it a strong choice for classification tasks like diagnosing diabetes, where features like glucose and BMI may have complex relationships with the target. I call fit on X-train and Y-train to train the model, allowing it to learn how features like glucose and age distinguish diabetic from non-diabetic patients. Once trained, I make predictions on X-test with predict, storing them in Y-pred, and evaluate with accuracy score and classification report. The results are decent. Accuracy score 0.7208 to 72.08% correct predictions, or 111 out of 154 samples. The classification report details: for non-diabetic, precision 0.79, recall 0.78, F1, score 0.78, support 99. For diabetic, precision 0.61, recall 0.62, F1, score 0.61, support 55. Macro average F1 score is 0.70, weighted average 0.72, moderate performance, with better detection of non-diabetic cases. I use Morris sensitivity from Interpret's black box module to explain our model's behavior globally. The Morris sensitivity method is an explainability tool that measures feature importance by perturbing inputs and observing how these changes affect the model's output. In this case, the predicted probabilities. It uses the elementary effects method, where it varies one feature at a time across its range, calculates the change in prediction, the elementary effect, and repeats this process multiple times to estimate the mean effect, mu, and standard deviation, sigma, for each feature. A higher mean effect indicates greater importance, while a higher sigma suggests the feature's effect varies depending on other features, indicating interactions. I initialize Morris sensitivity with our model's predict-proba function to get probability outputs, xtrain as the background data, and the feature names from xcolumns. I generate a global explanation with explain global, extract the feature importance data, and print the results. The global feature importance scores are BMI 0.2745, the highest, indicating it's the most influential feature on diabetes predictions. Glucose 0.2360 follows closely, showing its critical role. Skin thickness 0.1119, age 0.0962, and pregnancy 0.0873 have moderate influence, while diabetes pedigree 0.0806, insulin 0.0804, and blood pressure 0.0590 have the least impact. The visualization likely shows a bar chart with BMI's bar at 0.2745, followed by glucose at 0.2360, and shorter bars for blood pressure at 0.0590, providing a clear ranking of feature importance. Let's dive deeper into these outputs. They're a diagnostic roadmap for diabetes prediction. The first row showed a patient with pregnancy 6, glucose 148, BMI 33.6, age 50, and target 1, diabetic, while the next had glucose 85, BMI 26.6, age 31, and target 0, non-diabetic, suggesting higher glucose and BMI are associated with diabetes. Accuracy of 0.7208 means 72.08% correct predictions, 111 out of 154 test samples. The classification report confirms non-diabetic has precision 0.79, recall 0.78, F1, score 0.78 for 99 samples. Diabetic has precision 0.61, recall 0.62, F1, score 0.61 for 55 samples. Moderate performance, better for non-diabetic cases, possibly due to class imbalance. The Morris sensitivity results are insightful. BMI at 0.2745 and glucose at 0.2360 are the top drivers, aligning with the head's diabetic patient having BMI 33.6 and glucose 148, both high values. Skin thickness 0.1119 and age 0.0962 also contribute, with age 50 in the diabetic patient supporting its role. Pregnancy 0.0873 makes sense with 6 pregnancies in the diabetic case, while blood pressure 0.0590 being lowest aligns with its value of 72 not standing out. Diabetes pedigree 0.0806 and insulin 0.0804 being low is interesting. Insulin 0 in the head may reflect data issues, but pedigree 0.627 suggests some genetic influence. Morris sensitivity's global view helps us prioritize features for diabetes risk assessment, highlighting BMI and glucose as key factors. To conclude this health research study, we've analyzed the Pima Indians diabetes dataset, a 768 sample study of Pima Indian women, and trained a random forest classifier, achieving an accuracy of 0.7208 and a macro F1 score of 0.70. The global explanation via Morris sensitivity revealed BMI and glucose as the top drivers of diabetes predictions, providing a clear ranking of feature importance. Random forest classification's ensemble approach captured complex health patterns, and the Morris sensitivity method's perturbation-based analysis offered transparency for our black box model in this binary classification task. Grab this code, experiment with feature engineering, and dive deeper into diabetes prediction. I'm inspired by this health analysis. Hope it sparked your interest in data's role in medicine. See you next time for another impactful data journey.